Good evening, everyone. It's a great pleasure to have Professor Bažant here. Professor Bažant, if you are in the engineering field, you should know he's a towering figure. And with all the achievements I listed there, it's a bulletproof. And each of the bullets, if everyone gets one of them, it's a lifetime bragging right. But he got all of them. And I keep short, and so you take a look at it. Today we're going to listen to some interesting study from Fishnet statistics and how to use it to safe design our concrete structures or biomimetic materials. Is that right? Yeah, let's now enjoy Dr. Bažant's talk.
Thank you, Shinda, for this very nice introduction. It's great to be invited to this university, but it's even better to be invited twice. It means I didn't do bad last time. But I would like to call attention to one problem which has been underestimated in engineering, namely the true nature of safety that are required for engineering design, namely safety of the order of 1 in a million. And I must say that in this work I had an outstanding collaborator, Wen Luo, who did all the computations and also helped me with in analysis, and of course sponsors. The problem of safety is not that old in the mechanics, structural mechanics. The area in civil engineering came first in 1960s, where Alfred Freudenthal is considered the father of structural safety in civil engineering. Now, I would like to mention also that my career echoed his. He studied in Prague, got all his degrees in Prague. He started his career by designing bridges, same as me. And then he escaped a nasty regime, Nazism in his case. I escaped too, but in his case it was life-saving. And designed Port of Tel Aviv engineering structures. They came to Columbia University and did a fantastic work over the years, which combined equally mechanics and probability. If you look at his papers, collected papers published, they are about equal. Now, after him, as I see it, there will be a 50-year schism. At one side, advanced probability was combined with simplistic mechanics. So you come to conferences like ICOSAR or ICASP, they are very sophisticated, low statistics, random vibrations, and seismic spectra, statistically and so forth. But they don't solve more than an elastic plastic beam or maybe portal frame. On the other hand, come to computational mechanics, they have very advanced mechanics and computations, but simplistic probabilities. Stochastic finite elements cannot give you more than coefficient variation. You need far more than that. So they does not answer the problem of safety. So my point in this lecture is that what we need is a tail risk design. And why? There is lots of literature on risk that we should tolerate from engineering side. So it is believed, it is always emphasized that engineers must not increase the risk to which people are normally exposed. So we have, of course, risks such as being hit by lightning. Nobody cares about that. Being eaten by a crocodile or being by a falling tree. That's less than 1 in a million, all these risks. We must exclude terrorism because terrorism also kills by frequency less than 100 a year, which is less than 1 in a million, but the possibility that it would expand to 1 million is there, so that's a different subject. On the other hand, driving a car, we cannot do anything about it, but the risk is 1 in 100. You have a chance of 1 in 100 to die, to finish your life in a car. Anyway, so this is what engineers have to satisfy, and that's extremely challenging, how to predict that. Now, I would like to point out this diagram. Probability from 0 to 1, load. Plot two distributions. Gaussian distribution, this curve, Weibull distribution, for the same mean, same coefficient variation. Now, look at the difference. The distance to the point 10 power minus 6, this is not 0, that's farther, is about double, can be even more depending on variation from the mean for Weibull distribution than for Gaussian. Now, if you have a embrittled steel, you know the distribution is Weibullian. In fact, it's verified by 8 years of experience with metallic airframes. So if you know it, then it's enough to know variation, and you know you are here. If you know the failure is Gaussian, which is obvious if all the elements of the failure surface must be mobilized at the moment of failure, you know variation, you know you are here. So in these problems, people didn't care much about it. But then came quasibrittle materials, and in quasibrittle materials, it can be anywhere in between. It depends on size, depends on type of material, depends on material architecture, and it is a major question. What people don't quite appreciate, that you have a material which is stronger in the mean, so this is now not cumulative, but density of probability, CDF, cumulative density, PDF, probability density function. So you can have two materials. I will mention Fishnet statistics type for nacre, and then one is material is 80% stronger than the other, and you get exactly the opposite as a tail, 35% difference. Now, should we design for the mean? No, because for safety we care only about this. We don't care about the mean. And this some should be noted in material science, civil engineering labs too, that we should somehow investigate how it behaves as a tail. And that can be, of course, controlling material architecture. All this affects that. Now, how to do that? So to verify empirically probability of 1 in a million, you would need to do 100 million test repetitions. So imagine breaking 100 million aircraft wings, or even 100 million test specimens. That's beyond what we are able or willing to do. So you must have a theory, and this theory must of course be verified by some way, but not by repeated testing, it's histograms, by some other way. So far there have existed only two theories. The weakest link model has been always considered infinite, and then it goes to Weibull distribution. By the way, Weibull distribution was actually discovered by a mathematician Fishnet 11 years earlier, but it's named back to Weibull, who verified it. We showed some modification of that for many materials to consider finite change, not infinite number. That makes a difference, significant difference. And the second model is fiber bundle. Imagine two rigid plates and brittle or any kind of fibers in between, and calculate the distribution, and that has been shown always goes to Gaussian distribution, no matter what is the behavior of the links. Now I will show here, the screen is somewhat shifted, no, I don't know, it's a little bit missing here. There is a third model which is solvable analytically, namely alternating longitudinal and parallel links, and it looks like a fishnet. Actually occurred to me on a tennis court. I called it initially the tennis net model, but fishnet is shorter, like a fishnet put diagonally, and that can be solved analytically. The history of this problem is long. The first person who thought about statistical side effects and distribution was actually Mariotte, known in physics, the 1600s. But the problem was debated. Every famous scientist said something about it, Young and so forth, until more than 30 years later, Weibull got it right for brittle materials. He came with Weibull distribution and verified by tens of thousands of tests. Amazing. Although Ronald Fisher actually mathematically discovered that before in Cambridge. And then there's Daniels, the other model, also in Britain, which I don't have photo. So why the problem becomes now prominent? Because we have so-called quasibrittle materials which have brittle constituents, but inhomogeneity size is not negligible. It's large. So in concrete failure, the process zone size length is about 1 foot. So you don't see fracture phenomena in this kind of beams. But if you go to a reactor vessel, you go to a dam, it becomes a major thing. But what is nice about concrete, because it's easily seen in the lab, we argued about it, but similar behavior you see in tough ceramics, in, this is dying too actually, in fiber composite rocks, rocks, bones, CIs, rigid foam, dental ceramic, dentine, cartilage, many biomaterials, snow, board, carton, and nanotubes, of course, and all the materials, brittle materials, become quasi-brittle if you go to scale of micrometers, MEMS, microelectrode devices, and then the question arises, what is the distribution? And of course, the 10 power minus 6, 1 in a million, applies not only to aircraft, but bridges, MEMS, microelectrode devices, same thing. And so these are materials which exhibit non-negligible material characteristic lengths, which is the length of the fracture process zone, basically. And what is interesting is that at the increasing size, when the size is getting bigger and bigger compared to the material characteristic lengths, they transit from ductile behavior to brittle. And the low deflection diagram changes, small, large, you have a size effect and all that. All right, so I will discuss this for one type of size effect. There are actually two types of size effect in quasibrittle structures. Type 2 is essentially deterministic. It occurs when a stable crack can grow large before the maximum load. So in concrete structures, if you load a concrete beam, you grow a crack, 80% of the crack is not falling. It is still stable. And most reinforced structures are like this, and then you get this kind of distribution, which, by the way, now 35 years later is coming into ACI code. I will not talk about this. I will focus on distributed type 1. The specimen becomes unstable as soon as you form full fracture process zone and macro crack starts to propagate. So this is still damage zone or fracture process zone. And crack starts going from here, and that's the moment of failure. So it can be considered deterministically, and behavior is like this. If you add statistics, you find out eventually it goes to Weibull statistics exactly. This is a plot in log-log space. The power law is a straight line. Logarithm of load, logarithm of size, Weibull law, Weibull statistics is a power law, so it's a line of constant slope. So I will discuss only this failure and this kind of failure. Statistics is extremely important. These very small sizes, and very often we have to consider this. So let me first review briefly some results obtained over the last about 12 years. So how to approach it? There is a theory of Freudenthal who derived the distribution by considering the statistics of critical size flaws, maximum flaws. But if you look at it, it's a correct theory. It really relates one scale of flaws to another and derives one set of properties from another set, another assumptions. The only way the probability is known exactly is the atomistic scale. And the reason is that as the atomistic scale, frequency of the breakage of bones is equal to probability of the breakage of bones exactly. You might object, what about impact? It goes very fast, right? So in impact, you break atomic bonds at the frequency of 1 billion 10 power 9 per second in impact of a missile into a bunker. But there are 10 power 14 thermal vibrations, random vibrations per second. So on the average, atoms vibrate how many times? 14 minus 9 is 5. Vibrate 10 power 5 times, 100,000 times, and then there's this jump. Then the bone is lost. So that's quasi-stationary. So probability is exactly equal to frequency. That's the only scale. So we looked, that's a decade ago, at propagation of a crack through an atomic lattice. It's similar in disorderous materials. And it has to, before you advance the open crack, has to advance through the lattice. Has to advance through the lattice by steps, obviously. So it's either here or there. And this discrete motion superimposes undulating potential on a smooth potential which you normally derive for this nanoscale zone. So the total potential decreases as the displacement of the crack grows, is superposed, and now the main point here is that these ways are numerous, in fact thousands maybe to go down, so difference between the valleys is very small. Now what is happening is that we can imagine a loss of the bond rupture means that this atom gets out of equilibrium position, jumps over and comes to the lower equilibrium position. But it's happening both ways, also backwards, but this frequency forward is bigger than forward. So there is a Kramer's rule in transition theory and chemical thermodynamics is used for chemical reactions, which gives you the frequency as an exponential of activation energy divided by Boltzmann constant and temperature constant. So this activation energy now jumps forwards, have a reduced barrier by half of this. There are backwards increased barrier, so these are more frequent. Obviously, if these exponents are not very different, it goes to a sine hyperbolic. And you can show, I leave out lots of calculations here, that sine hyperbolic argument is very small. And that means that sine hyperbolic can be replaced by a linear function. Linear function of the argument is this. This is stress, applied stress, remote stress square. And this is a thermal term which is multiplicative. The main thing is this, it's a power law. So the distribution, the tail distribution is a power law. All right. So now this is on the atomistic scale. Now, Weibull distribution has a power law tail, but the power law tail is typical exponent between 20 and 60. So how do we increase the exponent from 2 to 60? And that's because of scale transitions. Now in scale transitions, what do we have? We have a macro crack, it is a process zone that has many micro cracks. Each micro crack is process zone much smaller, that has again many micro cracks, and so it goes. In concrete it goes 7 orders of magnitude, in metals about 4 orders of magnitude. And the failure or propagation then requires what? So a micro, you can imagine a process zone where this is already formed open microcrack. Microcracks are obviously mostly aligned in mode 1 loading, and they have a tendency to localize, so that acts like a chain if they always localizes to failure at one point. And there are some other microcracks which are constrained laterally by compatibility condition, and that behaves like a fiber bundle. All right, now we work on this, consider some models which give this transition. So this is one model which we simulated and calculated, that you have various types of series and parallel couplings, and what has been shown, it takes a lot of asymptotic calculations, Laplace transform, but it has been proven that power law is always preserved by these systems, and in series coupling the exponent is raised but additively. So one element here is tail exponent 2, 2 have 4, 3 have 6, and so forth, and in a chain they are preserved, but penetration of the power law tail changes in the opposite way, and the only possible way to explain what we see is that it's alternating series and parallel connections. Many connections series, many parallel, and that's how we can explain what we see on a larger scale. So the result of these calculations, I am leaving out what is in a number of papers over the last 10 years, that if we plot the distribution in a Weibull scale. Now, you know this normal probability paper, right? The normal distribution appears a straight line. So also Weibull paper, Weibull distribution is in that scale gives a straight line. This is a transformation of the probability of failure, and this is the size in logarithmic scale. This is Weibull distribution. And now we get it for one representative volume element, one curve, and when we consider structures which have so-called positive geometry fail as soon as one processor fails, not every structure does it, reinforced concrete not, then we need to calculate the failure probability of structure as a whole. So we consider a chain, and basically what we are doing, 1 minus failure probability is survival probability. So imagine put it on one side. And that structure survives if all the representative volume elements survives, the joint probability. So, and these are identical. There is an exponent and the number, but it must be scaled by stress. I will not talk about this. This is probability of 1 RVE. Now, if you take this to infinity, and if you know that this probability is a power law, you get this Weibull distribution. But for quasi-bit structures, you cannot do that. You must work with this. And what it means is that you have a Weibull distribution for small size, and again it goes to Gaussian, and one can show the transition is relatively fast. And if you have 10 RVEs, still small structure, this point moves exactly up, the intersection point, exactly up, and that's a mathematically proven rule. This n must take equivalent, because if the stress is 80% of the maximum, its contribution about 1,000 times less than the maximum. So in homogeneous stress, all elements contribute, in inhomogeneous often not. Now, how do we get this transition point, which is essential? And does the transition occur at probability of 100, 1,000, whatever? That can be obtained from side effect. Now, you can solve from this. I will not go into details. What is the side effect law? Now, if it's Weibull, has been shown long ago, side effect must be a power law. So now we plot logarithm of load versus logarithm of the size, measured by the number. Power law is a straight line. And by the way, in side effect, and this is the beauty of it, we need to consider only means. The mean is easy to test. You can test maybe 4 sizes, you need 6% for each size, so it's not very, very large. Now what you see is this. If you change the grafting, the point of transition from Weibull to Gaussian, this is Gaussian Weibull plot, then you find out the side effect is similar but shifts along this line. And if it's the side effect will shift at 1,000s, 10,000 here, 1,000s, 100s, and see the what the experiment show. Now, interesting that for all quasi-bit similitudes, the transition is about 1,000s. So that's empirical. We could not predict it, but it's empirical. And it's easily tested, and from this actually you can infer back what is the distribution. Now there is another interesting point. This Weibull distribution, which is shown here, is typically considered in engineering as sigma minus constant. And the argument is intuitively, we know that for low enough stress it will never fail, right? But do we really need it? Now if the exponent is typically like in concrete 24, in some metals 30 to 50, if the exponent of this law is so large, and if the stress is 1/3 of the maximum, you will find out that the break to occur, you would need to wait 100 times longer than the age of the Earth. Okay? So we don't need a threshold. In fact, you can show that if you consider a threshold and go this argument back, you will conclude that Kramer's rule and Boltzmann statistics doesn't apply. Then it must have a constant. It's impossible. But this is what's mainly used in the literature. So our conclusion is no threshold, and transition from the on the RVE scale, representative volume elements, is at about this value. We work out a similar theory for tunneling in computer dielectrics, computer chips, then it's about 1 million. But it's a very different physics, of course. So the question is now, how do we predict changing from Gaussian distribution to this distribution on the structure scale based on what we see on the small scale. So let me now show some typical test results. The biggest set of experiments, amazingly, was obtained in 1930s in Stockholm by Weibull. He tested 10,000 specimens of concrete, more of steel, more of ceramics, and obtained these histograms. So this is plotted in Weibull scale. So Weibull is a straight line here. For brittle steel, for ceramics, obtain straight lines only. But for concrete, this is concrete, he obtains these curves. And you see how amazingly smooth these histograms are. Normally you don't see that. That's why, because each point is an aggregate of 100 tests, the average amount. If you put individual tests, it will be jumping up and down. There will be some scatter. And also here, we verify that the transition which occurs from side effect, you get at this point, and we plot it perfectly. People try to, the fit improves if you put threshold. In fact, Weibull pointed it out himself, but you fit it a little bit and then it does not work anymore. This is a set of composites from NASA, where they concluded in this testing by Jackson that Weibull modulus is variable, that it depends on structure size and structure shape. Impossible. That's a material property. That's denying even boundary value, value problem and so forth. But we can, we of course have to normalize it for different materials, have different constant here, but it perfectly agrees. I don't say it proves, but no disagreement. We can perfectly fit all this with one Weibull modulus and with zero threshold. And you can even find a formula, asymptotic matching formula, which describes that. Now these are some more recent paper on various ceramics, porcelain, dental composites, silicon carbide, silicon nitride, so forth, taken from recent literature, and they all observe these deviations. If you plot it in Weibull scale and you plot the total stress, okay, you observe these curves. It is interesting to note that the exponent of the Weibull part are high, like 40. That size effect in the mean is actually 1 over this exponent. Size effect would be size exponent 1 over 40, very small. And indeed, size effect is very small in these materials. But what they do, they fit it by distribution with a threshold. I'm sorry, this somehow it's cutting bottom of every slide. I don't know. There is sigma u threshold here. Now, if they plot it in that scale, they get also straight lines. But you see how compressed these diagrams are. The coefficient variation is actually higher. But they are in principle incorrect. That can be seen if you consider extensions and if you consider the size effect. So in Weibull scale, I take this data from this picture by Santos. These are the data. Of course, some points are aggregate several points. And this is what being done in most literature. They put a threshold, they have this curve. And then if we extrapolate it by our way, the grafted Gauss-Weibull distribution with the transition, you obtain this diagram. Now, this is a transform scale line of 1 in a million is this dashed line. You see enormous difference. The difference from the mean goes from 21% to 41%. Enormous difference. And this is what matters for structural safety. So, I mean, this cannot be used. Now, imagine a side effect. So, in terms of side effect, this is the size of testing. And in ceramics, they say we tested actual size. We are not interested in side effect. But the difference is enormous. If you expand the 3-parameter Weibull distribution of Santos, you get this curve. If you extend it according to our model, it agrees here, but it's a straight line, and you see the enormous difference here. You might say this specimen is too big. That's actually 1 billion RVEs. But under uniaxial tension, let's say a prism under uniaxial tension would be what? 1000 RVEs this way, 1000 this way, also the other way. If the RV is 1 millimeter or 1 micrometer, you easily realize it. If it's a positive geometry, structure becomes unstable after the failure of 1 RVE. That's what's happening, and this is the error. So I mean, this has been published already almost 10 years ago, but there is no response in the ceramics community to this. I would like to mention one case of many cases where this made a difference. So we analyzed in detail the failure of Malplassat Dam in France in 1959, which was the tallest and thinnest arch dam in the world. It failed at the first filling. And this is what it looked afterwards. That this flood wiped out totally the town of Fréjus, several hundred people dead. What we can say today is that if it were designed today, based on this kind of analysis, the tolerable movement of foundation would be about 51% smaller. Every day a dam is designed for some foundation movement. It's never zero, right? Is it 1 millimeter? Is it 1 inch? Is it 1 foot? In this case, they underestimated the schist, which slipped on the south foundation. The dam was subjected to bending, and the bending is exactly this brittle fracture case, where that's why it failed. The theory has been extended to cyclic and static fatigue. Now then you have to another case. You need to realize that if you take lifetime, right, and fatigue until failure, crack grows, but grows subcritically. So it's not a question of tail in the mean. And we have a well-known law, Paris law for cyclic loading, or Charles Evans law for static fatigue. So you can again imagine in concrete it looks like this. There's nanoscale particles, but no order in crystal material like this. You need to integrate it over a cycle, and then how you go and you obtain a law by the integration that advance of crack is again proportional to square of the imposed stress. Now what has to be noted here, that again all these cracks at the one scale have subcracks, or a smaller scale that has subcracks until you go to nanoscale. It's impossible to calculate exactly, but we can argue about the tails again simply. But here we must argue a different way. It's subcritical. So it's not a question of failure, it's a question of dissipating the same amount of energy for unit advance of the crack or over unit cycle on the macro and micro. And if you impose this condition, then energy dissipated on macro and micro, you conclude again that the tail is growing, and that you get from this distribution with a square of exponent, you get to higher values for concrete about 10. Same kind of behavior. And then you can calculate lifetime. So these are fatigue lifetime for histograms for ceramics of various materials. You see for lifetime same behavior. If the structure are perfectly brittle, lifetime in will be Weibull, so it will be straight line in this scale. Why? Because again the structure fails where the first element fails, right? So it's like weak statistics. But what is observed in quasibrittle materials, there are these transitions which you can fit exactly. You see that the exponent now is not 40, it's very small, and that means for lifetime the size effect is extremely large. In fact, it can be shown that the size effect of the Weibull exponent for lifetime, this is analytically derived, is Weibull exponent for short time divided by n plus 1. N is the exponent of the subcritical growth law. So Charles Evans law, or in cycling it would be Paris law, which is the order of 4 to 12, something like that. And this is one case where we can verify it. There are not many tests, but Bunsen-Sturgar tested with on the same material, aluminum oxide, short time strengths, slope 1 over 30, will be very small side effect. So 30 to 1, very small side effect. Here the side effect would be 1 over 1.1, extremely large. Both are fitted with the same law, and this is verified by this analysis. My former student, Jean Langlais, who is in Minnesota teaching, as associate professor, tested at Sandia with boys. Similar problems on the for polysilicon on the MEM scale. They use chain slack tester, which is generally used for this, testing many specimens on loading. You see again the same behavior. In Weibull scale, you don't get a straight line, you get a curve. That's verified here. And they tested side effect, and this side effect is shown here. It's not a straight line like with Weibull, it's a curve. So in actually a micrometer scale, every material is quasibrittle. So now let me get to the new result, which is not in my book, which came out 1.5 years ago. It's a result of last about 15 months. The Fishnet statistics. So inspiration comes this way. We know that nacre, the iridescent material of the shells of abalone or some other mollusks, has extremely high strength. The strength of this material is 10 to 20 times larger than the strength of constituents. It's mostly CaCO3, aragonite, kind of limestone. And these animals produce a nanoscale microstructure consisting of rigid platelets of aragonite, something like this, which are typically about 5 to 10 micrometers long, about 20 to 30 nanometers wide, so they are longer than shown, and they are bonded by a biopolymer, very thin layer of few nanometers, 20 nanometers. So how to simplify it? Here is a micrograph of this structure. This is naked abalone shell. So we have rigid elements, and under longitudinal loading, which is what is of interest here, not transverse loading, you have to transmit the force by shear from this platelet to this platelet, and then to this. So the force transmission looks like this, and it looks like a fishnet put diagonally. Okay. Now the question is, as it can be solved, it can be solved, and it can be also easily simulated. My student runs millions of simulations. We actually use in MATLAB, we use the program for a truss. Initially we propped it so it does not collapse, but it makes no difference statistically. We let it collapse to a line, but this connectivity is there, and that's how we obtain the results. Now, how to approach it analytically? So, differently than Weibull distribution, or fiber bundle. We consider survival probability, which is 1 minus failure probability, and it would be a sum of a number of terms where this corresponds to survival with zero failed link. It means it fails when the first link fails in the fishnet. One link fails here, and there is a redistribution. This has higher stress, more stress, then it goes to no redistribution of stress. Now then there are links where one link failed before failure, it means failing as a second link. That's distributions where survives with two links and fails as a third link. So these are events which are disjoint, independent elements. It's really, in probabilistic terms, a union of disjoint sets. And that proves it must be a sum. Now what is interesting about this sum, that these terms decrease rapidly. There are many failures with first link, second, This is much bigger than that, and you really don't need more than about 4 terms. Even 3 terms is enough. So, and that can be calculated quite well. So calculation involves some redistribution, which I mentioned here already. If this length, if one link fails, this is higher stress, then it decays. We replace this with a continuum, which goes to Laplace equation. We calculate continuous redistribution and then project it into the mesh. So we get the calculations. And we consider fishnets of rectangular size with m rows and columns, like this. And the simplest calculation is we consider up to 2 terms. So first term is one link, one link fails, 0 link before. That's Weibull distribution, weakest link model. Survival occurs if all links survive. This is probability of failure of one link, and this is so this is probability of survival. And if there is n of them, the joint probability gives product. Now, for the second term, we can argue similarly. It can start at any of n points. There are n elements here in the fishnet, and that must happen simultaneously with survival of the rest. So we have survival probability is this difference, 1 minus failure probability, and it must occur jointly. So n, but you must distinguish elements which are redistributed, which are not. So that's all calculated, and you can reinterpret it by putting it in the form of Weibull distribution with a correction term. This is the correction term which is easily calculated, and so that's a second order approximation, we'll say, with 2 terms. With 3 terms it's more complicated. So you have now if 2 elements, 2 failures, 2 links fail before reach maximum load when the third is failing. So this is this term. So you must here distinguish 2 cases where the second term is second failure, the third failure is second right next or at a remote place. And I will not go into the discussion, but everything can be reduced to joint probabilities and this summation disjoint sets. For one or the other, you have to think about it carefully, of course. It makes no sense to explain a lecture in a minute. And but what I want to see, that the calculation is not difficult of the second term. It's just simple equations. We can calculate third term, but that's several pages. I never tried 4 or 5 terms, okay? That's too difficult, but you don't need it. Look at this result. So what Venlo did, he simulated these fishnets in MATLAB, such that for each case he ran 1 million simulations. I would have preferred 10 million at least, but it was good enough. This is the line of 10 power minus 6, and these diagrams are good up to about here, about 10 power minus 5. This is becoming too scattered. Now each of these points is an aggregate of 10,000 simulations, okay? So it's very smooth. It's virtually exact probability distribution. So this is the analytic 2-term fishnet. This is simulation. It means we exclude all failures where more than 2 links failed. And then this is the 3-term fishnet. It matches very well. If you let any number of failures to occur before overall failure, you get this line. You see how close it is? For most practical purposes, it's good enough. So we cannot get actually analytical solution exactly for any number of ways, but we get very close enough analytically and in a simple way. This is again the line of 10 power minus 6, and you see the enormous saving. So if you compare to weakest link model, okay, positive geometry structure failing because of one element, you get this. If we can induce the fishnet action, it means this alternating series parallel, you get from 70% to 74 to 35% away in terms of safety. It's a 4.45 increase, enormous enhancement of safety. What I leave out at this point This is median, mean is somewhere here. There is another degree of safety, of course. Many people, Gao, Suo, Hutchinson, my colleague Espinoza, many people calculated over the last 20 years, explained why in the deterministic terms, which means mean, these structures are so safe and so much stronger. But you get far more by taking into account the material architecture. And that makes an enormous difference here. All right, so here I show the distribution, the power law tail, the typical load displacement curve. This is the spread of damage from the simulations. This is the same thing in CDF, probability density function, the tail consideration. Again, analytical prediction compared. But let me point out now the gain in terms of probability. So before I showed the gain of strength, probability being fixed at power minus 6. Now in terms of probability, the conclusion is that with 210 Fishnet you decrease the probability failure 25 times. So enormous contribution to the failure, to the safety of the material, with 3 times somewhat more. Now an interesting point is the Fishnet is this. You can change the shape, this square in this case. You can increase the number of rows, decrease the number of columns, you get a bundle. 2 rigid plates and fibers in between. The opposite, if you extend it longitudinally, you get a chain. So Fishnet statistics provides continuous distribution from Weibull to Gaussian distribution. That's shown here schematically. If you change from a chain to a bundle, how the distribution changes in Weibull scale. This is Weibull distribution, and this is Gaussian distribution in the same scale. Now it has been very careful computationally when Lo did it. Each point is 10,000 simulations, and that's here we move from 2 times 28 to 128 times 2 from chain to bundle, and you see this continuous transition. It is not superposition of these two simulations. It's much more. It's very different actually. If you would try to put a partition of unity combination of these two distributions, would be incorrect. It will be very different. Now, interesting is the role of scatter. Actually, very interesting. At low scatter, the peak load occurs very early, typically the first element. If there is no scatter, positive geometry, it would fail with one link. That's it. But as the scatter increases, peak load happens after much damage, as you see here. These are actually simulations of this Fishnet you see here exactly. So high scatter may weaken the material in the mean, but can make the tail very much safer. Very much safer. So this is a very useful property to know. So sometimes scatter is good actually in these materials. We should not aim at most homogeneous structures. Now this is a side effect that we compute. So it's similar to this type one that I showed beginning, but it is somewhat different. For brittle Fishnet, it's actually a curve which is an envelope of asymptotes which corresponds to 1 link, 2 links, and so forth being failed before maximum load. What is interesting that as you change the size, distributions change or rotate about 1 point here, generally. And this corresponds in the size effect curve to transitions from one to the other asymptote. Now some latest results over the last 4 months. Actually, paper just occurred on this. Another question is, if we have this staggered platelets arrangements. So I assume that the bond between these two fails as soon as the cracks forms and it runs dynamically through the length of the connection of the, between the two platelets through the biopolymer. but that's not clear. It may work in a cohesive way, that you propagate a long crack and then it becomes dynamic. And if there is a long crack, what it means in practical terms is that the transmission of force in one link is not up and straight down or nearly straight down, which is perfectly brittle, but gradual softening. And there can be various slopes. Eventually it can go to zero slope, which will be plastic link. All right, so one needs a somewhat different approach. This previous analysis would not quite hold. So what we do, we assume the link goes down, but it goes down in a series of jumps. And that greatly simplifies the analysis. Typically maybe 20 jumps. So jump down, you can reload, get to this curve, it becomes dynamic, and so forth. So series of jumps. And then on the whole fishnet produces behavior like this. And that changes depending whether you have vertical drop or not. It changes very much the behavior. In one case, a distributed damage, you know, and goes suddenly. And how to approach this? So the series of jumps means that we don't get failure from one jump. Right? We need a number of them. We may need 20 jumps down, and then we don't need the minimum strengths. We need the case minimum, where K can be some 1/3 modulus minimum, or 5th modulus minimum, 10th modulus minimum. Now this is a subject of a well-known theory, order statistics. All right, so the probability of failure is then probability of how many jumps you have going down, which is a random number itself, and the probability given that number of jumps, K, conditional, case minimum, that sigma is given, then the arguments, then the load, K. So order statistics, there's a book on it, which is several books, gives you some formula, which is not difficult. That's here, how to calculate it. And for distribution of the number of jumps, you have, this is like arrival statistics. Actually, it's a geometric Poisson distribution. It's another formula. So that's what we discovered by reading more literature on this kind of behavior, and we put it into calculations. And then, using order statistics, we find the following. This again, Weibull scale, Weibull distribution. You have one jump down. It fails. This is perfectly brittle. This is 10 jumps down. And the point now is which of these distributions take. And there is a simplification also. If there is one big jump down, there is a bigger distribution of stress. If there are 20, it's very small. And after the next jump, it actually takes into account the previous jump. So you can forget about a distribution with order statistics. There's a great simplification analysis. And with this, we can calculate what happens. And in order statistics now, okay, this gives the same thing for the number of jumps down. And in this plot, how we determine which corresponds to minimum maximum load. In this case, you have no load deflection diagram. So how to estimate what is the maximum load? Is it this curve? Or is it the 5 or so? Okay, eventually we looked at the nominal stress change with the number of damage links. And at the beginning, it works, everything coincides, and suddenly they diverge. And we find that this divergence always corresponds to maximum load. So that tells you, in this case, that the number of jumps down, which gives maximum load, is 20, not something else. And this is now verification by numerical simulations. Again, very extensive calculations, and they also give this kind of behavior. And you see the effect. that there is a 50% tail strength increase at the probability line of 10 power minus 6. Sorry. It's again a very significant effect even for these fishnets which are progressively softening. And these are what when low fitted distributions. They are skew, of course. And further comparisons for different slopes of the softening. Small slope here to big slope, different behavior. And how to determine side effect. Now from side effect you can go back to distribution. Now we found this very simple property. It is difficult to judge what if you enlarge geometrically the fishnet, enlarge both lengths and width in the same proportion, which is the definition of side effect. But we split it into two kinds, that we enlarge it longitudinally and here enlarge it laterally. Longitudinally, you see that in the middle you keep the same slope, same Weibull modulus, but deviates earlier. And then actually we can put into simple formulas. And if we do transverse scaling, interestingly, all the distributions rotate about 1 point. And I can actually show that it has to be about 1 point. So here you have positive side effects. Structure is bigger, it is weaker. But if you give the transverse scaling, the opposite happens. Now which one wins? You must put these two together. And if you put them together, you see this picture. Still there is an intersection point, but it goes to a low probability, not being here, somewhere low. But it can happen, and probably often happens, that positive side effect in the mean, or this is median actually, you see the structure is getting weaker as it becomes larger. Changes at 10 power minus 6, which would be, wait a minute, this is not probability scale, it's about here. We can have opposite side effect in the tail. So structure which has a significant variation gets opposite behavior. And we can get this way, we can approximate a reasonably good formula for the mean, for the median, sigma 0.5. It would be better to do mean, where mean is actually much harder, but they are close enough. So this is our latest work, which is just being published. We just finished a paper on this. And our last comments that you have also effects of rate, and that changes behavior totally. This is work of Minnesota for using the Fishnet model for aluminum nitride, and we obtained enormous also analytically for the rate effect. These are the formulas that we obtained. Okay, so I think it's time to sum up. So I would like to make 3 points. We need to focus on tail risk design. Mean is mostly not what we want. We want safety. And if it's temporalistic, it's of course very, very challenging. Now what I didn't talk about, but it's in this book, that in civil engineering the safety factors are determined from reliability indices, and the reliability indices need a correction. In civil engineering, people learn about corner reliability index, Haushofer-Lind, but they are based on Gaussian distributions. And these distributions are different, and there is a significant difference to these indices, which has been worked out. And finally, I would like to point out, experimentally in histograms, we have no data below 0.005. So you need to go 3.5 orders of magnitude down to get to 10 power minus 6. The only way to check it experimentally to predict side effect and then argue indirectly. And that's the only way to determine it analytically. Now finally, many of you probably are in computer analysis. So if you have quasi-brittle materials, not brittle steel, then the architectural and biomimetic effects like nacre make enormous difference. So for concrete, rocks, wood, toughened ceramics, fiber composites, the error in safety factors is much bigger than any error from deterministic analysis. Much bigger. And obviously, why? Because the devil is in the tail. So with this, I would like to thank you for listening. And if you want to learn more, I have a book which you can look at. Fishnet is not in it, because it was published 1.5 years ago. The idea occurred at the time. It will be the second edition, but everything else is in it. And there are some sequence of papers we can freely download from my website. Thank you.
Any questions for Dr. You want to take the questions? Any questions for Dr. Bažant?
So you must have been an expert at different trials where they've had some failures and why it failed. And how do you, when you're in court, explain what you just said?
I never go to court. It takes lots of time.
It does, I know.
And people who go to court
Your
don't.
students go to court.
Maybe some do, yes, actually. Yes, this of course is probably beyond what the court experts would normally consider in front of the judge, I think, this kind of reasoning.
I was gonna
But eventually it has to be translated into design rules, design codes.
Right.
And then it can go into the court, right? They would not believe this. It's a good point, of course. Yeah, probability plays a big role in many disasters, of course, and that's where you actually have this 10 power minus 6 limit. In fact, there is a statistics that large concrete structures have been historically failing at the rate of 1 in 1,000, not 1 in a million. And there are statistics. There is a Melcher's book says that Nordic Committee for Nordic Beton Komitet for concrete structures concluded the same. Now, why doesn't it cause any uproar? Because there are not too many large structures. So it happens about every 5 years, right? Some major failure like that bridge in Venice or that sort of things. But then imagine a guy who has to go over the bridge every day. He has the probability 1 in 1,000, which is terrible, which is much worse than what we should tolerate. Bridge in Minneapolis, same thing. People who drove over the bridge every day are exposed to that. So you cannot neglect this. And in Gauss there is a serious problem, partly why? Because they didn't cause a side effect. Now in the new ACI code, they are including now side effect 2 35 years after it was proposed. That will happen probably in ACI convention and it will be voted on for sure now in March, at the end of March, this month. Okay, so yes.
So the Fishnet statistics, if you want to use it to characterize a material before you use it, does it increase the requirement for test numbers, test specimen numbers?
But if you want to do it by histograms, repeated testing, enormously, forget it. Okay. You need to test size effect.
Yes.
And so size effect you can indirectly argue what is the behavior. And that's true also for Weibull statistics or Gauss-Weibull. That's the same thing. It can all these histogram testing of ceramics actually superfluous. If we know it's Gauss-Weibull, we can derive it from size effect with much fewer tests. Lifetime testing, you don't need to wait to lifetime. You can derive it by measuring exponent of Charles' law or Evans or Paris law and combining with short time Weibull, and you get lifetime. So that's why we need to calculate, of course. Yes. That's a very good point which I didn't mention, yes.
Great, thanks.
Any more questions? Well, if not, I'd like to offer you a small token of appreciation for your lecture, and we want to thank you very much, Dr. Bažant. Thank you.
Thank you very much, yes, I appreciate it. It was very nice. Very nice.
Thank you. Thank you. I hope there are some sandwiches left for those who are very hungry. Bon appétit.
Merci.